you ever wondered what happens deep underwater, far beyond what we can see? Scientists have discovered a dangerous underwater crack that might cause the biggest tsunami in history. This is due to something called turbidity currents, which are not ordinary events and have caused a lot of excitement among scientists worldwide. But what exactly are these turbidity currents, and could they affect us? Let's find out. Picture a hidden world beneath the waves where rivers of sediment flow like liquid avalanches, shaping the seafloor and affecting marine ecosystems in amazing ways. Turbidity currents are rapid downhill flows of water made denser by large amounts of sediment. They can be triggered by earthquakes, collapsing slopes, and other geological disturbances. Imagine a river flowing underwater, carrying a mix of sand, silt, and clay, creating a cloudy, moving underwater dust storm. These currents play a crucial role in shaping our understanding of Earth's history. The layers of sediment they leave behind act as a geological archive, giving us clues about past environmental conditions, climate changes, and seismic events. Researchers from the Monterey Bay Aquarium Research Institute discovered that a layer of sediment-rich water moved rapidly over the seafloor, stirring up the upper few meters of sediment. They observed plumes of sediment-laden water during these events, which they believe are secondary to the main flow of seafloor sediment. Typically, turbidity currents start on sloping ground, where sediment-laden water flows downhill because it is denser than the surrounding water. The driving force behind these currents is gravity acting on the dense, sediment-filled water. These semi-suspended solids make the sediment-bearing water denser than the surrounding water. As these currents flow, they stir up the ground, picking up even more sediment, which increases their density and speed. This process scours and erodes the seafloor. When an oceanic turbidity current reaches the calmer waters of the flatter abyssal plain, the sediment settles out, creating a deposit called a turbidite. One significant event was the 1929 Grand Banks landslide off the coast of Newfoundland, Canada. Triggered by an earthquake, this undersea landslide created a huge turbidity current that reshaped the ocean floor and caused a tsunami, resulting in shipwrecks, damaged undersea cables, and 25 fatalities. Another major event was the 1964 Great Alaska Earthquake, which triggered underwater landslides and turbidity currents. These currents reshaped the seafloor and left a significant geological impact. In 1979, the Milo landslide off the coast of Sicily triggered powerful turbidity currents that reshaped the Mediterranean seabed. These events, hidden from the surface, had far-reaching consequences, including reshaping underwater landscapes and leaving geological records that scientists study to understand Earth's history. Grand Banks landslide in 1929, off the coast of Newfoundland, Canada, one of the earliest documented turbidity currents in modern history, occurred in the North Atlantic. On November 18th, an earthquake triggered a massive undersea landslide, setting off a colossal turbidity current. This underwater avalanche, laden with sediment, raced down the continental slope and transformed the ocean floor. This event, known as the Grand Banks landslide, left a lasting mark on marine science. The turbidity currents from the Grand Banks landslide were extraordinary. Their impact extended beyond the hidden depths, reaching the surface and affecting human activities. Maritime records tell of shipwrecks, damaged undersea cables, and the devastating tsunami that resulted, causing widespread destruction and tragically claiming 25 lives. The ocean, often seen as calm, revealed its capacity for dramatic upheaval. Another significant event occurred in 1964, when a colossal seismic event rocked the Alaskan coastline. On March 27th, the Great Alaska Earthquake, with a magnitude of 9.2, the most powerful earthquake ever recorded in North America, struck beneath Prince William Sound. This quake sent shockwaves through the earth, triggering underwater landslides in the fjords and submarine canyons off the Alaskan coast. This chain reaction left an indelible mark on the ocean floor and highlighted the powerful interplay between seismic activity and underwater geological processes. Imagine the seabed shifting, underwater mountainsides collapsing, and massive amounts of sediment breaking free from their ancient moorings. During the 1964 Alaskan earthquake, these powerful currents raced down the submarine canyons, a subaqueous spectacle unseen by human eyes, yet profoundly sculpting the seafloor. In the years following the 1964 event, scientists embarked on a journey to unravel the secrets hidden in the sedimentary aftermath of these turbidity currents. They discovered that these currents weren't just sculptors of the seafloor. They preserved a record of past geological events and environmental conditions. Influence of turbidity currents. So, aside from causing tsunamis and other dangerous natural disasters, what do you think about turbidity currents? Do you think they have geological significance? How about their impact on climate change? What benefits do they bring to nature? Scientists began mapping the ocean floor in the 1920s using echo sounders, which measure water depths using sound waves. Echo sounders use sonar technology. The sonar showed that the ocean floor has dramatic physical features, including huge mountains, deep canyons, cliffs, and wide plains. It might interest you to know that the ocean's crust is a thin layer of volcanic rock called basalt. The ocean floor is divided into several different areas. The first is the continental shelf, a continent's nearly flat underwater extension. Continental shelves vary in width. They are usually wide along low-lying land and narrow along mountainous coasts. The shelf is covered in sediment from the nearby continent, and some of the sediment is deposited by rivers and trapped by features such as natural dams. Some areas of the ocean floor have deep, narrow depressions called ocean trenches, which are the deepest parts of the ocean. Now, returning to the topic of turbidity currents, they indeed have significant geological importance. By transporting sediments from continental shelves to the deep ocean, they contribute to the formation of sedimentary layers that record Earth's geological and climatic history. These layers help scientists understand past climate changes, sea level fluctuations, and tectonic activities. Turbidity currents can also influence marine ecosystems. They help in the distribution of nutrients across the ocean floor, which can support deep sea life. However, they can be destructive, damaging underwater cables and pipelines, and posing risks to offshore structures. In terms of climate change, the sediments transported by turbidity currents can bury organic carbon on the seafloor, potentially impacting the global carbon cycle. This process can sequester carbon and influence long-term climate regulation. The ocean plays a crucial role in regulating climate and weather through several processes. It acts as a massive heat sink, absorbing and storing large amounts of heat from the atmosphere, helping to regulate global temperatures by mitigating temperature extremes. The ocean absorbs a significant portion of atmospheric carbon dioxide, CO2, a process known as oceanic carbon sequestration, which helps mitigate the impacts of rising CO2 levels on climate change. Turbidity currents transport large amounts of organic matter and sediment. When this material settles on the ocean floor, it can serve as a sink for carbon, a process known as carbon sequestration, which helps regulate atmospheric carbon dioxide levels. While this doesn't directly address climate change, understanding carbon dynamics in the ocean is crucial for comprehending the broader carbon cycle and its role in Earth's climate system. Turbidity currents can also affect ocean circulation patterns. Changes in ocean circulation play a role in redistributing heat around the globe, influencing regional climates. While the direct impact of turbidity currents on climate change is minimal, their interactions with ocean currents can indirectly contribute to variations in heat distribution, affecting weather patterns and climate systems. Alterations in ocean circulation patterns can influence climate regionally. Changes in sea surface temperatures, ocean currents, and heat distribution contribute to phenomena like El Niño and La Niña, influencing weather patterns worldwide. The most common cause of tsunamis is underwater earthquakes. When tectonic plates beneath the Earth's crust move, they can generate seismic activity. Subduction zones, where one tectonic plate is forced beneath another, are particularly prone to powerful underwater earthquakes. The sudden vertical displacement of the seafloor during these earthquakes sets in motion a large volume of water, creating tsunami waves. Volcanic eruptions, especially those occurring beneath the ocean, can also displace water and generate tsunamis. When a volcanic explosion occurs, it can cause the overlying water to be pushed upward, creating waves that propagate across the ocean. In conclusion, turbidity currents play a crucial role in shaping the ocean floor and influencing geological and climatic processes. Their geological importance, interaction with ocean currents, and role in carbon sequestration make them a fascinating subject of study. If you enjoyed diving into this underwater adventure with us, don't forget to like and subscribe for more fascinating explorations.